So this is Cryptography, Lecture 4. And if you read in Chapter 1, there is a discussion about symmetric ciphers and asymmetric ciphers. So in a symmetric cipher, Alice and Bob, Alice is trying to communicate to Bob, Bob is trying to communicate to Alice, and they want to do it in such a way that their communication is secure, and their enemy Eve, who eavesdrops, cannot figure out what they're saying by intercepting their messages. And in a symmetric cipher, Alice and Bob have the same key for encryption and decryption. So what's an example? We have a Caesar cipher, where if we're using the English alphabet, there is a key, some number K, and the letter, whatever letter it is, A, is encrypted as the letter I don't want to confuse the K with the letter. It's just as the letter A plus K. So for example, if the key is 3, when you're encrypting, A goes to the third letter after A, B, C, D. B goes to E. C goes to F. Right? You go, right? X, W goes to Z. X goes to A. Y goes to B. Z goes to C. It's like you have the alphabet, and then under it, you translate this by 3. B, C, D, by 3 would be D, E, F, and so forth. When you get to X, Y, Z, that's A, B, C. So if you know what the key is, you're translating by a certain number 3, then you know how to encrypt, and you decrypt by sending each letter A to A minus whatever the K is. So if you get the letter D in the encrypted, in the ciphertext, you know that is A in the plain text. And this is symmetric. Both Alice and Bob know the key. They have symmetric knowledge. And that is one kind of cipher. Now, if Eve intercepts the ciphertext, she can try every translation. There are only 26 translations, and she will actually be able to figure out what message makes sense, and she'll be able to decipher the text. So this is not the world's greatest cryptographic method. In fact, it's one of the worst, but it is symmetric. This is one example of a symmetric cipher. What is another example of a symmetric cipher? Well, you fix a prime number P, and suppose your ciphertext, your plain text M, that you want to transmit, your message is M. So you choose a number, let's try and pick the same notation that the text is using. K, no, K is good enough. Choose K with the greatest common divisor of K and P equal to 1. And your encryption is C sub k of m, given the and m is every text is a number. We don't use letters as text. Texts are numbers. And so if you take your plain text m, you let this be equal to km mod p. This is encryption. And decryption, you choose L such that LK is congruent to 1 mod p. Every non-zero, every integer not divisible by p is a unit mod p. And your decryption method, d sub k of c, is multiply c by L. Let's see, mod m. And then you can see if you start with the message m and you encrypt it into c sub k of m, which is congruent to km mod p, and then you decipher, you decrypt c sub k of m, that's lkm mod p, but lk is 1, so this is just 1 times m, or m mod p. So you recover your message. So this is encryption. This is decryption. And again, here's Alice. Here's Bob. Alice has a message M she wants to send. So she encrypts it. And what she sends is the message C. And then Bob decrypts it. So M goes to C. C goes to M. And Eve, who intercepts the message, finds C, but she doesn't know. She can't decrypt it because she doesn't know K or L.
Professor, can you move the paper down a little bit?
Yeah.
Oh, thank you.
So Alice has a message M. She encrypts it by whatever symmetric scheme, for example, multiplying by K mod P, sends the message C. Bob retrieves it, multiplies it by L mod P, and recovers M. Eve gets C, but if she doesn't know the key, she cannot find what M is. But you'll notice that one disadvantage of this scheme is that if Eve learns just one pair, MC, so she doesn't know the key, but she knows that there was a message M and it was encrypted as C, then Eve can break the code. Because Eve knows that there exists some K such that C is congruent to Km mod P. So she knows C, she knows M. If you know M, you can find the inverse of M mod P by the Euclidean algorithm. So K is M inverse C mod P. So knowing one message and how it's encrypted enables Eve to break the code. So that is one disadvantage of this code. By the way, I should point out, if you're not familiar with this, because you may not be familiar with it, there's a standard method built into most computers to convert text that involve words and numbers, letters and numbers and punctuation marks and so forth into binary digits, binary numbers. There are lots of ways to do it. One is the ASCII code. Let me just find this in the text. Mm-hmm. see what this is. Oh, there it is. Share the screen with this for 1 second. So you should see on page 39, this is the ASCII coding scheme. So it assigns to every capital letter a number from 65 to 90, the 26 capitals. For every lowercase letter, a number from 97 to 122. But these are written in binary. So every number up to 122 certainly can be written as an 8-bit binary number. A bit that has 8 zeros and ones is called a byte, B-Y-T-E. Here are the numerical values for space, parentheses, apostrophe, and dot. So you can write any text as you have your text with numbers, punctuation, and whatever. You write every character as a binary number, 8 bits, and you end up with some big, long binary sequence, which is the message you want to encode. This is one way, not necessarily the best way, certainly not the only way, to convert a message into a number. But a lot of computers, at least a while ago, use this standard encoding scheme, it's called ASCII code. And you take your binary string and you break it up into blocks of a certain length, not too big, not too small, and you send blocks of binaries, and every block is a number. You take the binary string, convert it to a number, you get a number. So every message you want to send that you're going to encrypt and decrypt is going to be some positive integer. And this is one reason why you deal only with integers when you're doing encryption. You don't need to deal with words, letters, anything of that sort. Okay, this is a symmetric. These two examples I just gave, the Caesar code, when you shift the alphabet by a fixed number k, or this arithmetic code where you multiply everything by k and reduce mod p. P is a large prime, k is relatively prime to p. The sender and the receiver, Alice and Bob, both have the key, and that allows them to use the cipher, the code. But there is a kind of a problem, which is how do they get the key to use? So at some point, you have Alice and Bob, and maybe Alice has the key. Bob does not have the key. So somehow Alice has to send the key to Bob. But she can't encode it because Bob doesn't have any way to decode it. He doesn't know what the code is. So there is a problem about how does one party in an encryption scheme send the key to the other without Eve, don't forget Eve, Eve is eavesdropping constantly. If Alice sends the key to Bob, Eve will know the key. That's not very good. And one solution to this problem is to try to develop an asymmetric cipher or code. In an asymmetric cipher, Alice and Bob do not have the same encryption, decryption information. It's not equal. It is asymmetric. And maybe Alice knows how to encipher. So Alice has the key to encipher, but only Bob can decipher. So it may be Bob sends to Alice the enciphering key, and Eve can intercept that. So Eve knows how to convert a message from plain text to ciphertext. But Alice, knowing C, and Eve, knowing C, do not know how to decrypt the message, but Bob does. So the first question is, do asymmetric ciphers exist? Is it possible to invent an encryption method which does not in itself allow decryption? And this was a big problem, an unsolved problem in cryptography for a long time. The text gives a very simple example of an asymmetric cipher. An asymmetric cipher, so in an asymmetric cipher, everyone, the public, knows how to encrypt, but not how to decrypt. Here's a trivial example. Bob wants Alice to be able to send him a message, but no one else knows how to decipher the message. So, in fact, Bob wants anyone to be able to send him a secret message that only he can figure out. So Bob says, okay, in the town square, I put a safe with a slot. And deposit your message in the safe through the slot, and only Bob knows how to open the safe. So anyone can come along, blah, 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 go to the safe, take their message on a piece of paper and stick it in the safe. Anyone can do that. But no one can open the safe except Bob. And that's how he gets the messages. So that's an example of an asymmetric cipher. The encryption is put your message in the box. Decryption is know the combination to open the box. But Alice, anyone, no one knows the combination except Bob. So this is an example of an asymmetric crypto system, if you like. Anyone can send Bob the message secretly, but only Bob can decipher it by opening the safe. Now, this is kind of a baby example, but it gives you the idea. In this case, the public knows. And such a system is called a public key crypto system. Because what is public is the key to encrypting, but knowing how to encrypt does not allow you to decrypt. That's the nature of a public key crypto system. Now, an example of a system that does not work is the following. So this is a bad system. Choose a large prime P. Choose K such that the GCD of K and P, greatest common divisor, is 1. Encryption. The message M by M goes to whatever KM is congruent to, mod M. And everyone knows K. So here's Bob. Here's Alice and everyone else in the universe. He sends her K, the key. So if Alice has a message M, she computes KM mod P, calls that number C, and sends C to Bob. But that's not secure because Eve knows K. Everyone knows K. And Eve knows elementary number theory. So with the Euclidean algorithm, anyone, including Eve, calculates L such that LK is congruent to 1 mod P and decrypts C by multiplying C by L, and that gives you back M mod P. So this is a public key crypto system, if you like, in the sense that Bob tells the public, tells the world, you encrypt by taking your message and multiplying it by K and reducing mod P. But it's not a good system because anyone can break it. So this is not a public key crypto system is a system in which anyone can encrypt, but no one except Bob can decrypt. So this is bad. And what we discussed yesterday, and I'm going to go through again today, is a great public key crypto system. I have to explain how it works and why it's great. And this is called RSA for its discoverers, Rivest, Shamir, and Edelman, the RSA crypto system. So it's very similar to this bad system, but of course it has to be a difference because this is bad and this is great. In the bad system, we chose a large prime P. In the good system, all we do is choose 2 primes P. So choose 2 different large primes, P and Q. Or I should say, Bob. This is what Bob does. Bob is creating this public key crypto system. So Bob chooses 2 large primes, P and Q, and these are secret. That is, Bob chooses them, but he doesn't tell anyone. Now, Bob knows P and Bob knows Q. So if you know P, you can subtract 1, and you know P minus 1. If you know Q, you can subtract 1, and you know Q minus 1. And you can multiply those two numbers together. So you get a big number. And lots of numbers are relatively prime to this. So you choose an encryption key. Let's call it E for encryption. You choose any integer E, and there are tons of them. If P and Q are big, millions and millions of them. Choose E such that the greatest common divisor of E and P minus 1, Q minus 1 is 1. See if there's a homework problem. I could use that. So Bob chooses 2 primes. He doesn't tell anyone. That's his secret knowledge. If he knows P and Q, he knows how to subtract and multiply those numbers, P minus 1, Q minus 1. And it's easy to find numbers E that are relatively prime to P and Q. And Bob publishes, he tells the world, what are the following 2 things? N, which is the product of P and Q, and E. So here is Bob. Here is Alice. And here is Eve, eavesdropping on them. So Bob has numbers P and Q, but what he transmits to Alice is this number N and this number E, that pair of numbers. So Alice knows N and Eve knows N. And the encryption method you start with plain text M, and you compute M raised to the power E and reduce it mod N. And that number C, you choose C congruent to M to the E mod N. So C is between 1 and N, certainly. That's your ciphertext. So Alice knows M, but what she sends to Bob is the number C, and Eve intercepts it, of course, and knows what C is. Now, how does Bob take C and find M? Well, because E is relatively prime to P minus 1, Q minus 1, this means E is a unit in the ring of integers mod P minus 1, Q minus 1. So Bob, so this is the decryption method. Bob computes a number D such that ED is congruent to 1 mod P minus 1, Q minus 1. If E is relatively prime to this modulus, it has a multiplicative inverse. There's a number D, such that ED is congruent to 1 mod P minus 1 Q minus 1. And then Bob takes the message M and he computes the number M prime, which is C to the power D mod N. Okay. Everyone knows N. Everyone knows C, but only Bob has calculated D. And what is C to the D mod N? So let's just repeat the calculation we did yesterday. If ED is congruent to 1 mod P minus 1 Q minus 1, this means that ED is equal to 1 plus P minus 1 Q minus 1 times something K. Right? ED minus 1 is divisible by P minus 1 Q minus 1. So ED is 1 plus P minus 1 Q minus 1 to the K. And we know that C and P minus 1 Q minus 1 are relatively prime. They have greatest common divisor 1. So C to the P minus 1 Q minus 1 is congruent to 1 mod P minus 1, mod PQ. Remember, we had proved that mod P, if C is relatively prime to P, C to the P minus 1 is congruent to 1 mod P. And if C is relatively prime to Q, C to the Q minus 1 is congruent to 1 mod Q. So C to the P minus 1, Q to the minus 1 is congruent to 1 mod both P and Q. So C to the P minus 1, Q minus 1 minus 1 is divisible by P times Q. This is Fermat's theorem and Euler's theorem. The congruences. So M prime is congruent to C to the D. C, what is C? C is M to the E. This is M to the ED. What is ED? ED is 1 plus P minus 1 Q minus 1 K mod PQ, which is M. Which is M to the first power times M to this power. M to the first power is just M. M to P minus 1 Q minus 1 is 1. This is 1 to the K. This is congruent to M mod N. And we're done. Bob is done. Bob has deciphered the message. So what did Bob do? Let's just repeat this because this is really very important. Bob picks 2 primes and doesn't tell anyone what they are. That's his secret knowledge. And if he knows P and Q, he can certainly multiply them, right? I mean, just take 2 numbers and multiply them. That's N. And you can also subtract 1 from each of them, P minus 1, Q minus 1, and multiply that. That's P minus 1, Q minus 1. And knowing this big number, there are many numbers relatively prime to it. Just choose one, call that E. And now what you publish to the world, what you tell everyone, is what is capital N and what is E. Everyone knows that, including E. And if you know those 2 numbers, Bob says, here's how to send me a secret message. Here's how to encode your message. Take your message M, raise it to the power E, and reduce it modulo N. So that C be congruent to M to the E mod N, C between 1 and N. Anyone can do that. That's the encryption of your message M, and send that to me. So Alice wants to send Bob the message M secretly. She does this arithmetic, gets the number C, sends C. Bob recovers C, and because he knows P and Q, and P minus 1, Q minus 1, just by the Euclidean algorithm, he can compute a number d where ed is congruent to 1 mod p minus 1 p minus 1. And if he takes the ciphertext C and raises it to the power D mod N, that recovers the message M. So Bob can do that. The question is, why can Eve not do that? So what is it that Eve knows? Eve knows N. Eve knows E. Everyone knows that. And everyone knows C. So Eve knows N, E, and C. But to decipher the message, Bob knows D. If you know D, you can decrypt every message. And what is D? D is the inverse of E mod P minus 1 Q minus 1. So Eve knows PQ, which is N. She doesn't know what P and Q are, but she knows N. And she knows E. To compute D, must know not PQ, but P minus 1, Q minus 1. Or you must know P and Q, which means you must be able to factor N to find P and Q. And then, this is what gets the star, factoring is hard. Doesn't mean it's impossible. You can take your number N and divide it by 1, 2, 3, not 1, not 2, it's going to be odd. 3, 5, you can just divide it by numbers until you find a factor. And you're bound to find a factor. The only problem is how long will it take? And if N is very big, these trial divisions, dividing by 3, 5, 7, and so on, if it takes 100 billion years, doesn't do you any good, you're dead. So factoring is hard. In practice, it's impossible with our current state of knowledge and current technology. Factoring is hard implies RSA crypto system is secure. I should emphasize it's not provably secure because no one can prove that someone in somewhere isn't smart enough to figure out a new factoring method that works. But so you can't prove that no one is smart enough to solve this problem. All we know is no one has solved this problem, and huge amounts of government and private money in every country, every technologically advanced country in the world have gone into studying this and trying to do it. And everyone failed. So that is RSA. This is asymmetric. Bob and Alice do not have equal or symmetric knowledge. Bob knows P, Bob knows Q, Alice does not know either one of them. So this is an asymmetric cipher. The encryptor and the decryptor do not have equal knowledge. It's asymmetric.
So Professor, it's kind of like so like Bob tells Alice to encrypt like a message in a certain way, and then Alice encrypts it, and then she sends the encrypted message back to Bob.
Yeah, exactly.
Okay.
But Alice does not know the method to decrypt a message that's encrypted in this way.
So, so like yeah, because Bob knows basically knows like both. Bob basically knows like how to encrypt and how to decrypt it. He sends it to Alice, and then Alice sends the encrypted message, and Bob's the only one that knows how to decrypt it, so he
Right.
gets the
The
message.
asymmetry is that knowing how to encrypt a message doesn't tell you how to decrypt a message.
Okay.
So in the Caesar cipher, where let's say every letter is turned into like the next letter three over,
Yeah.
if you know how to do that encryption, you know how to decrypt. Because when you
Hmm.
receive a message, you send every letter to the one that's three back.
Yeah.
So that's completely symmetric. Knowing how to encrypt tells you how to decrypt. But in this case, so far at least, knowing how to encrypt does not tell you anything about decryption.
Okay.
Okay. Okay, let's see. There's one other point that um, this is just a little piece of arithmetic, which is interesting. So Bob computes and sends. He knows and he transmits P times Q, this number N. And to break the code, you must know P minus one, Q minus one. Now, if you know this, then you can find from E, you can find D. If I just multiply this out, this is PQ minus P minus Q plus one. This is N minus P minus Q plus one, or N plus one minus P plus Q. So what this says is, so E knows N, and then she knows N plus one. If E knows P plus Q, then Eve knows P minus one, Q minus one. So she can, just from this formula, everyone knows N, everyone knows one. If someone knows the sum of the two primes, then you know what this is and you can break the code. So breaking the code it's enough. It's not necessary to factor N. It's enough to, though, be able to figure out to say, if N is P times Q, then I know P plus Q. And knowing P plus Q is as hard as factoring. That's the point of this. So if you know P plus Q and PQ, you can break this code.
So Professor, just to reiterate, like the whole point of this is that like what's it, you can know N, but like the what's it, the factoring part is that you there's so many different like values you can get for P or Q. You don't know like the right one. Because
No,
like
no,
it's hard.
no. It's not that there's only one value for P and one value for Q. There's only
Yeah.
one way to factor N.
Okay. Yeah.
That's the fundamental theorem of arithmetic. Only one way that this can be done,
Mhm.
but there's no way to find it.
There's no way to find it because the numbers are so large, and factoring takes a really
So
long
just
time.
right. So just factoring, just dividing one number after another into N and trying to find the number which leaves a remainder of zero
Hmm.
would take forever.
Okay.
Okay. Let me do some of the homework problems just to, because I think this is a good point to stop for what we've done this week. But we've actually covered quite a bit of material. And let me
Yeah, I
find,
saw that professor that you updated our homework assignments to include some exercises from chapter 3.
yes,
Okay.
yeah, because
And
this is
chap
definitely on the midterm exam next week.
and chapter 3 is the RSA system, right? Just to
Well,
make sure.
there's more to it than RSA, but the first parts of sections 1 and 2 of
Hmm.
chapter 3 are RSA.
Okay. And we're gonna be getting into like the other like parts of chapter 3 starting next week.
Chapter 2.
Oh, chapter 2. Okay.
But because we had I spent a lot of time developing elementary number theory. And the point is that this is what is used in cryptography. And I want to give an example, a very important example of how you use the number theory in cryptography. That's the point of this, of all of this. So let me see if I can find my assignments. I have to have them somewhere, so I'll get them. Cryptography. Okay, here we are. So a couple of the problems refer to the mark 1.9 multiply. So let me see if I can find that. It's just explaining a little bit, since your calculator generally doesn't deal with integers, if you do division, it gives you decimals. Interesting. So let me try and find a better problem. Yeah. Okay, good. So in the homework, 1.9 and 1.10, those exercises have to do with the Euclidean algorithm. So let's start with 291 and 252. So to find the greatest common divisor, 291 is 252 times 1, and it leaves a remainder of 39. 252 is 39, I think, times 6. That's is a remainder of 18. Divide 39 by 18, that goes in twice. And leaves a remainder of 3. Divide 18 by 3, that leaves a remainder of 0. So the GCD of 291 and 252 is 3. And to write 3 as a linear combination of these two numbers, I think I'd actually done this one before, but it's always good doing things again. 3 is 39 minus 18 times 2. But 18 is 252 minus 39 times 6 times 2. So this is 39 plus 39 times 12. That's 39 times 13 minus 252 times 2. This is correct. I hope it is. And 39 is 291 minus 252 times 13 minus 252 times 2. So this is 291 times 13 minus 252 times 15. I doubt that this is correct, but plus 252 times minus 15. Let me just check. So 3 is 39 minus 36. 39 minus 18 times 2. 18 is 252 minus 39 times 6. So this is 39 times 13 minus 252 times 2. 252, so 39 is 291 minus 252. So that's 291 times 13 minus 252 times 15, or plus 252 times minus 15. So that should be okay. Let's try and find something more interesting.
Professor,
Yes,
can you please do B, please?
B?
If
Sure.
you, yeah, please, if you don't mind. Thank you so much.
Okay. So So that's more challenging because the numbers are a little bit bigger. So this is 1.9b. We want to compute the greatest common divisor of 16,261 and 85,652. So what do? We take 85,652 divided by 16,261. So let me use the method that you can use if you have a calculator. I actually don't have a calculator, but I have my computer, so I'm just going to use Maple as if it were a calculator. So let me see if I can share my screen with Maple. Share screen. Maple. Share. Okay. So you should see this Maple screen. So let's say I let A be equal to 16,261, and I let B be equal to 85,652. And if I do A divided by B, I get, oops, that's something wrong. 16,85,652. Let me do it the other way. No, let me do B divided by A. And I want to write this as a decimal. So on a calculator, this is what I would get. So that would say that 85652 is 85652 is 16,261 times 5 plus the remainder. Right? This is 5 plus something. So this is, if I take B minus 5 times A, that's the remainder. So 4347. And then I take 16,261 and I divide it by 4347. And I want to write this as a decimal, so let me just do it in one step. This is just the command in Maple to 3.74. So 16,261, it's 4,347 times 3 plus some remainder. And the remainder is 16,261 minus 4347 times 3. 16,261 minus 3 times 3, 4347. I get a remainder of 3220. Then I take 4347 and I subtract, oops, I take 4347 divided by 3220, that's 1.35. So 4347 is 3220 times 1 plus the remainder. And I actually just do that in my head, but let's do it continuous way. So 4347 minus 3220 is 1127. And then $32.20 divided by 1127 is 2 something. So 32.20 is 1127 times 2. And what is my remainder? 32.20 minus 1127 times 2, 966. And then 1127 divided by 966 is 1 something. So 1127 is 966 times 1, and my remainder is 1127 minus 966, and that's 161. And then I take 966 and I divide it by 161, and I get 6 evenly. 966 is 161 times 6. So the GCD of my GCD is equal to 6. So let me just stop the share if I can. So this is what I found. If I did everything correctly, 85,652 divided by 16,261, that goes 5 times, and that's the remainder. 16,261 divided by 4347 goes 3 times, and this is the remainder. 4347 is this plus 11. This is the remainder. I get these remainders, and I'm sorry, 161. So the last positive remainder is 161. And so 161 is the greatest common divisor. And let me just, let's see. Let's just double check. I started with the number 16,261. And I divide that by 161. And it's an integer, 101. And if I take 85652, and I divide that by 161, that's also an integer. So 85652 is 161 times 532, and 16261 is 161 times 101. So this is what we see. These are the two numbers I started with. This is 161 times 532. This is 161 times 101. 532 and 101 are relatively prime. So the greatest common divisor of these two numbers is indeed 161. So you don't want to do this by hand unless you have to, but you should have a calculator, if not a computer. And that's the way it works.
So good question, Professor. We're gonna be, what's it, for the midterm, it's mostly gonna be like GCD, there'll be some proof questions and also RSA also.
Well,
Are those, I'm not like mainly, but I'm saying, well, like, will those topics
Well,
probably
it certainly includes everything we did on congruences,
mm-hmm.
right? So that's more than greatest common divisors.
Okay.
Let's see, what's the rest of this homework? So we also had problems, let's see, 12, 15, 16.
Professor, can we use this problem to solve 110B, please?
Oh, that's just a lot more work because you have to work backwards, right? So,
Yeah, okay.
right. So,
That's, I see.
I mean, you can do this for a homework, but you can't do this for an exam because it would take too long, right? You would say
Okay.
161 is 1127 minus 966. That's 1127 minus, and what is 966? 3220 minus 1127 times 2. So this is 1127 times 3 minus 3220. But 1127 is 4347 minus 3220. So it's that times 3 minus 3220. So this is 4347 times 3 minus 3220 times 4. It's actually not so long. This is 4347 times 3 minus, what is 3220 times 4? 3220 is 16,261 minus 4347 times 3. So that's 4347 times 3 and 4347 times 12, so times 15 minus 16,261 times 4, and 4347, this is 85652 minus 16,261 times 5, all times 15, minus 16,261 times 4. So this is 85652 times 15, and I have 16,261. 5 times 15 is 75, and 4 is 79. So plus 16,261 times minus 79. So, it takes a minute to do, and then you have to check. I would always check I didn't make any mistakes in arithmetic. So I would check, and I even multiply this out to be sure. But that's all that you do.
Thank you, Professor. Thank you. I appreciate it.
Let's look at, let's say, 115. What's the multiplication table for the unit group? Z mod 9Z star. So the group of units, mod 9, are 1, 2, 4, 5, 7, 8. Okay. Z mod 9Z is 0, 1, 2, 3, 4, 5, 6, 7, 8. You cross out the ones that are not relatively prime to 9. That means you cross out 0, 3, and 6. And these numbers that remain are the units. So what is the multiplication table for the units? So you just have to do all the calculations mod 9. 1, 2, 4, 5, 7, 8. 1, 2, 4, 5, 7, 8. We're multiplying the mod 9. So 1 times anything is just the anything, it doesn't change. 2 times 2 is 4. 2 times 4 is 8. 2 times 5 is 10, which is 1 mod 9. 2 times 7 is 14, which is 5 mod 9. 2 times 8 is 16, which is 7 mod 9. 4 times 2 is 8. 4 times 4 is 16, is 7 mod 9. 4 times 5 is 20, is 2 mod 9. 4 times 7 is 28, is 1 mod 9. 4 times 8 is 32, which is 5 mod 9, and so on. You just fill in the table like that. So that's the multiplication table. And if you're going to do a modular computation, like this is like 116. So you want to do 347 plus 513. What is this congruent to? Modulo 763. So if you just add them, you get 0, 6, 8. And mod 7, you want to try and pick a number between 0 and 762. So this is equal to 97, I think. Because 860 minus 97 is 763. This is A. And if you have what is 153 times 287 mod 353. So you can go to your calculator or your computer or whatever you prefer, but 153 times 287 is 43,911. And if you divide that by 353, let's see what you get. 43,911 divided by 353. That goes in 124 times. So what is the remainder? It's 43,911 minus 24 times 353. That's 43,911 divided by 124. So that leaves a remainder of 139. Again, you can do this by hand, or you can do it on a calculator, you can do it on a computer. But in this course, computers and calculators are allowed and actually encouraged. So that's what it is. Let's see. 17 and 18. So 117, we want to solve some equations. So the first equation is 80, is easy. This is x plus 17 congruent to 23 mod 37. So that means x is congruent to 23 minus x plus 17, 23. So x is 23 minus 17, or 6 mod 37. We want to solve x plus 42 congruent to 19 mod 37. That means x is congruent to 19 minus 42. 19 minus 42 is minus 23. Minus 23 is plus 14 mod 37. So the answer is 14. Just check 14 and 42 is 56. 56 minus 19 is 37. So that's good. What about solving the equation x squared congruent to 3 mod 11? That's a little more complicated. So we want to solve x squared congruent to 3 mod 11. So all you can do is look at the squares. What are the squares mod 11? 1, 4, 9, 16, which is 5 mod 11. 25. 25 is 3 mod 11. So x is equal, is anything congruent to 5 mod 11? Because x squared is congruent to 5 mod 11. But usually if a number has a square root, it has 2 square roots. Let's see, what about after 25 comes 36? 36 is also congruent to 3 mod 11. So we also have 6 squared is congruent to 3 mod 11. So for x squared congruent to 3 mod 11, the solutions are all integers x congruent to either 5 mod 11 or x congruent to 6 mod 11. And you can check, those are the only two. If you square 7, 8, 9, and 10, you won't get 3 mod 11. So this has 2 solutions. What about D? Solve x squared congruent to 2 mod 13. So let's make a table x squared, and x squared mod 13. So you take the number 0 up to 12. 0 squared is 0, and 0 mod 13 is 0. 1 squared is 1, 1 is 1 mod 13. 2 squared is 4 mod 13. 3 squared is 9 mod 13. 4 squared is 16, that's 3 mod 13. 5 squared is 25, that's 12 mod, that's 25, that's 12 mod 13. 6 squared is 36, that's 10 mod 13. 7 squared is 49, mod 13 is also 10. 39 plus 10. Yeah. 8 squared is 64, minus 13 is 12. 9 squared is 81. Mod 13, let's see, 6 times 13 is 78, so that's 3. 10 squared is 100. What is that mod 13? 7 times 13 is 91, so this is 9. 11 squared is 21. Modulo 13, that's going to be 4. 12 squared is 144. Modulo 13, that's 1. There's no 2 here. So this equation, this congruence, has no solution. And so on. Well, maybe that's enough for now. But these are good exercises, and these are all basic problems in the number theory you need for cryptography. So you should be able to do this kind of arithmetic in order to do well in the midterm exam. Any questions before we go for today? Okay. Next class
Oh,
is,
excuse me,
yeah, go ahead.
Professor. My question was, you said that by like sometime next week, you're gonna maybe possibly make a review sheet for us to
Yeah, I
like look.
will. I will. It might
Okay.
have to be in two parts. One for the part for the material we did this week,
Hmm.
and then another part for the material we do next week before the midterm.
Okay.
Okay. Have a good weekend, all.